Welcome to the lecture number 27. In the last lecture, we have started with the fluorescence anisotropy, and we said we actually was doing the excitation of a molecule using a polarized light. Let me draw it once again. So, here is my sample cell containing molecules oriented randomly that I showed you, like these are the transition moment of these molecules. Molecular frame may be different, but this is just I am showing the transition moment, the direction of the transition moment. So, they are oriented randomly. So, it is like these several different types of orientations are possible. That is why this system, this condition is called the isotropic orientation of these molecules in the solution. Now, if I use a polarized light, the polarization, the direction of this electric field of this light, this is a plane polarized light, is oscillating only in this direction, and this is the direction of the propagation of light. Then, right. So, this is my polarized light, and I said that only those molecules whose transition moment is oriented along the polarization of this light, those molecules will be preferentially excited. So, let us now show you. So, this is my ground state, So, I write the isotropic orientation of the molecules. Now, with this excitation, and let us consider that this excitation is a delta pulse excitation, right. So, I just impose another condition, it will be clear to you, delta pulse, that means this electric field is present only for short time, there is a pulse excitation like we have seen in case of TCSPC or in the up conversion. So, immediately after excitation, because you know excitation takes a very less amount of time. So, after excitation the system will absorb the energy and the molecule will go to the excited state. Those molecules whose transition moments are parallel, right, to the electric field of the plane polarized light. That means, this guy and this one. So, let me draw over here. So, one will be here and there will be here, and there is here, and then let us say this one. So, another will be here, let us say this one, then another will be here, and where, let us say this one. So, another will be here. So, these many molecules are now promoted to the excited state. So, here I can write this is my excited state, and this is the anisotropic situation, anisotropic orientation. So, this is my excitation, right. Now, this molecule when it will come back from the excited state to the ground state, it will emit radiation, right. Obviously, it has some radiative non-radiative pathway, let us consider the radiative pathway. So, it will emit the photon, and the polarization of this photon in the early time will be along that particular direction. In that direction the molecules are oriented, that means the transition moment of the molecules are oriented in the excited state. So, the emission will also be in the same direction. So, in the early time the emission whatever you will get, the electric field of those emitted light will be like this. But as time goes, allow some time, these molecules will reorient themselves because of the random motion, right. So, this molecule will reorient themselves, and let us say after some time this molecule is like this one is like that, this one is like this one is like this, 1, 2, 3, 4, 5, 7 like this. So, now the molecules are like that. So, you have in this case the contribution of this vertical emission is reduced because only these two molecules are now present in this case, and you also got this type of emission, you also got this type of emission and so on. In other words, I can tell you that there will be some contribution in the horizontally polarized emission. So, there in this case only vertically polarized emission, but as time goes the contribution towards the horizontally polarized emission will increase. So, here I write vertically polarized emission. So, this intensity vertically polarized emission intensity, if I refer to as I parallel with respect to the excitation. Excitation is also vertical, emission is also vertical. So, this is parallel, and if this is the horizontally polarized emission, so this is horizontal and this can be referred as the I perpendicular. So, the condition as I said, it is now less anisotropic, and if you allow too much of time then all molecules will randomly reorient themselves. So, then it will be again the isotropic, but this isotropic is in the excited state, and in that from the excited state, from the isotropic condition, the molecule will emit fluorescence, molecule will emit photon, and those photon, like those electric field of those emitted photons, they will not going to be oscillating in a particular direction, not only vertical, but also horizontal and any other directions also depending on its orientation. So, here I write excited state but isotropic. Orientation. Now, if I replace this delta pulse excitation with CW excitation, delta pulse excitation and CW excitation means when I will use the CW excitation, then the condition is a steady state condition. That means the molecules will keep on going the excited state. Okay, by the way, let me talk about this time. If this time is shorter than the lifetime of the molecule in the excited state, then such kind of process randomization is possible. If this time is very slow, then full randomization of the orientation of these molecules will not be possible. So, there is some relationship that how much is this time compared to the lifetime of this molecule. If the lifetime of this molecule, let us say for example is 1 nanosecond, and this time for the reorientation time is 10 nanosecond, then the contribution of the I perpendicular will be much smaller than I parallel, because before the molecule will convert from this vertical position to the horizontal position, right. Later on we will see that it is not horizontal 90 degree, it is 54.7 degree, but that will come later. So, that for this reorientation will take more time than the lifetime. By the time it will reorient, the molecules are not in the excited state, it will come back to the ground state. So, the emitted photon will be like a vertically polarized light. However, if the reorientation time, like this time what I am talking about, this is actually reorientation time. If this time is much shorter than the lifetime, let us say lifetime is 2 nanosecond and this time, this reorientation time is 0.1 nanosecond, 100 picosecond, then immediately after you excite in the within 100 picosecond time scale, this is time constant, remember. So, the reorientation time in another 400 picosecond or so. So, all molecules will randomize, but the lifetime is 2 nanosecond. So, you will be able to see that after some time, right, after 500 picosecond or 600 picosecond, the intensity of this parallel and intensity of this perpendicular, they will be same. But now, when we excite with a CW light, that means we will going to integrate, right, the response from initial time to final time. So, this is a kind of a steady state situation, right. So, in this case the molecule will keep on go to the excited state and the excited state will deactivate, right. So, depending on this reorientation, right, I will get these two values are different. And anyway, this I parallel will be similar to I perpendicular, but it cannot exceed the I perpendicular, because you are exciting with this vertically polarized light. At most the I perpendicular will be equal to I parallel, and in the other extreme the I perpendicular will be 0 and I parallel is the maximum. So, these are the two extreme situation I could have. Suppose you are exciting this molecule, right, which are rigid, they cannot rotate, and you can make such kind of molecular system by embedding these molecules in a glass matrix. So, it is not solution anymore, it is solid. So, in solid how the molecule will reorient themselves, it is impossible. So, then you excite this molecule with CW light, you will only going to see the emission in this vertical direction. That means, the fluorescence light which is emitted from the system. What is my system? Molecules embedded in glass matrix, that means the molecule cannot reorient themselves. So, in that case the fluorescence will be polarized and that polarization is vertical, same as the excitation polarization. So, then the I parallel will be maximum and I perpendicular will be 0. And if you have taken this molecule in a solution where the viscosity is very low, there is no restriction, then after excitation the molecule will rotate. If the rotation is too fast, let us say for example it is ultra fast femtosecond, then once you excite immediately molecule can rotate. Molecule is actually rotating constantly, because nobody can stop. Molecule is rotating not because you are exciting, note it down. Once you are exciting some molecules whose transition moment is parallel to the electric field of your excitation light, those are excited and immediately they are rotated, because that is the inherent phenomena of this molecule. So, in that case the rotation is so fast that the contribution of this parallel and the contribution of this perpendicular, they will going to be same. So, whatever I said we can write this in terms of equation like this. So, I can define a term, this is called anisotropy denoted as R equal to I parallel minus I perpendicular by I parallel plus twice I perpendicular. So, you see this equation, in this equation it says that, right, when I parallel equal to I perpendicular, this quantity, when I parallel equal to I perpendicular, this R is going to be equal to 0, and when I parallel is much greater than I perpendicular, or I can say when I perpendicular is 0, right, or I can say for those thing I said rigid matrix, or for I perpendicular equal to 0, I can write R is equal to 1. So, the value of R ranges from 1 to 0. By looking at this value of R, I can comment on the rigidity of the system. If R is coming to be very high, it is very difficult to tell that R is 1, because it is not, but still I am telling. So, anyway, if the R value is let us say 0.4, it means that the reorientation is not that feasible. But if R is very small, 0.001, 0.005, that means the reorientation is very fast. So, qualitatively I can comment, and if you recall your Stokes-Einstein-Debye relationship, right, this reorientation depends on the size of the system. If size is small, reorientation is fast, size is large, reorientation is slower, and so on, right. So, this R can be directly related to the size of the macromolecule, which I will come later. Let us continue in this direction. Okay. Now, question is how I am going to measure this R, right, that is my question. Let us try to draw some experimental setup by which we will going to measure this R value. So, here is my excitation. So, this is my vertical excitation, and here is your sample, looks good, and emission is collected at the right angle, and I have emission monochromator and then I have detector where you can measure the signal when this is vertically excited, and then you will have two type of emission. One is like this vertical, another will be horizontal, right. So, I referred this as I parallel, just notation, and this one is I perpendicular. Now, when it will pass through, obviously this emission, right, will have some color, depends on the color of the light, right. So, that is why you have this emission monochromator, you can choose the color, right, and then it will be detected by this detector. So, when it will pass through this emission monochromator and will be detected by the detector, in detector I should get two value. For this I parallel I will get one value, for I perpendicular I will get another value. The question, how I will going to select? I have to put then that optical element, right, that optical device which is called the polarizer, right. So, for the generation of this vertical excitation light, because my light source is not polarized light, right, this is my light source, this is unpolarized light. So, once you use that kind of device like is called polarizer, I will not tell you the details of this, how does it work, I will just show you the use of it. So, this is my polarizer. Okay. To make this vertical excitation light from this unpolarized light source, you have used this polarizer. Now, this fluorescence again is not polarized anymore because of the reorientation under the constant excitation. So, both vertical and horizontal component and in between all those things, everything is there, but we are interested only in the vertical and horizontal, which is referred as I parallel and I perpendicular. So, to select whether I will take the I parallel or I perpendicular, I also need to use this one, right. So, let me draw this over here, let us say here, I have this polarizer, but generally it is called not polarizer, same thing, this one and this one, they are exactly same thing, but as you are using this to analyze the emitted light, so it is called the analyzer. Okay. Now, if you put this analyzer in this direction, you will get vertically polarized light coming out of this, other lights will be blocked. If you rotate it, rotate to like this, then the horizontally polarized light will come pass through, other lights will be blocked. So, in that case you will be able to measure I parallel and I perpendicular independently by setting the orientation of this analyzer, which is nothing but a polarizer. Okay. So, here is the vertical excitation and here is the horizontal emission, right. This is the vertical excitation, this is my horizontal emission and here is my vertical emission. So, in the detector what we are going to measure is these two intensities, either I parallel or I perpendicular. Now, as you know, as I already have discussed, right, when a particular intensity of light, that means a particular flask, photon flask is arriving to the detector through the monochromator. The monochromator has a specific throughput, which is obviously wavelength dependent, that we have discussed earlier. That is what all those emission corrected emission spectra, all those things comes into picture. So, when a particular intensity is coming through emission monochromator and then being detected at the detector, that value will be different, right. There will be some proportionality constant. I parallel, if it is 1000, obviously in detector you will not going to get 1000, it should be multiplied with some factor. Those factors are coming from the throughput of the emission monochromator and the detection efficiency of the detector, right, some, but that should be proportional. So, in this case let me write the intensity which is detected at the detector for this I parallel light as I parallel multiplied by that factor, sensitivity factor, I named it as SV, which is equal to your measured quantity at the detector, correct. So, let me name it as I, what shall I name? Let me name it as I VV, because here is my V and here is my V. So, that is why I name it as VV. So, I VV. Now, when you will set the analyzer for the detection of the I perpendicular, obviously that light intensity will be I perpendicular and that has to be multiplied with that sensitivity of the monochromator and the detector. So, I will write I perpendicular multiplied by the sensitivity of the monochromator and detector for the horizontally polarized light. This was for vertically polarized light. This is SV for vertically polarized light. But for horizontally polarized light, this sensitivity is not same as the vertically polarized light, they are different. So, here this sensitivity is for horizontally polarized light. Right, that is it, and I name it as I what shall VH. Here is my vertical and here is my horizontal. So, I am done. So, when I will write this I parallel minus I perpendicular, what I have to write? I have to write in terms of IVV and IVH, right. So, I have already defined this anisotropy R. So, now R will be written as I parallel minus I perpendicular by I parallel plus twice I perpendicular, is not it? But in the detector you are not measuring this, in detector you are measuring something else, you are measuring IVV IVH, that is related to I parallel when I parallel is multiplied by SV, and that is related to I perpendicular when the I perpendicular multiplied by SH. So, I will write this as I VV by SV minus I VH by SH, right. Here I parallel equal to I VV divided by SV. divided by I VV by SV plus 2 I VH by SH. Now, if I multiply both the numerator and denominator by SV, what will happen? Simply it will be I VV minus SV by SH into I VH divided by I VV plus 2 SV by SH into I VH. So, you see here this is your measured quantity, right. This IVV, this IVV is your measured quantity, IVH is your measured quantity. So, what you got, that IVV has to be subtracted with IVH when multiplied by with this factor. So, this SV and SH, this is fixed for a particular monochromatin detector, right, and this is a ratio of two constant. So, I can replace this ratio of two constant with one constant. So, let me write this as another constant I VV minus G I VH divided by I VV plus 2 GI VH. That means, whatever you are going to measure in the detector, you have to multiply with a factor. Whatever the value of IVH you will measure in the detector, you have to multiply with a factor. So, this is known as G factor. You have to multiply with this G factor, then only you will be able to calculate what is the value of anisotropy, otherwise you will not be able to calculate that. Now, my question is, how I am going to determine what is the value of G, right. That is my that is what we are going to do now. Now, let us consider that same experimental setup we are going to use, like you see here, this is the same, like this same experimental setup as I have shown over here, we are going to use. Let us write it over here once again. So, I am just writing a part of that, not the whole setup, because it is not necessary. So, here is your cuvette, and this right angle the emission is coming. I have two different polarization for the emission, and this is coming, and here is your monochromator emission monochromator, and then here is your detector. So, and here is your output signal. This is obviously towards this setup, this one means difficult here, na, because all the mouse pointer is not visible. Let us say this one is vertical, right. So, I can simply write this as V. I am just writing over here, this is V, and this one is horizontal. So, I am just writing here is H. Earlier what I have done, I have excited, earlier what I have done, vertically polarized light was used for the excitation like this. But now what I am going to do is little different. I will use like such kind of horizontally polarized light for the excitation. So, this is H. So, horizontally polarized light for the excitation. Okay. So, towards this horizontal excitation, this vertical, this V is I perpendicular. Simple. It is exciting like this excitation, this kind of emission perpendicular. Now, towards this horizontal light, this emission which is horizontal here, as I have shown horizontal, this horizontal means light is exciting like this way and emission is like this way. This is also perpendicular. So, this is also I perpendicular. Although this is horizontal, this is vertical towards what? Towards the monochromator and detector. Towards the monochromator detector, for the monochromator and detector, this one is vertically polarized light, this one is horizontally polarized light, but for this excitation light, both are I perpendicular. If both are I perpendicular, their intensity has to be same, right? And I already know that for vertically polarized light, that sensitivity factor of the monochromator and detector is SV, for the horizontally polarized light is SH, and then the rest of the things are easy. So, I can simply write the output signal in this detector and the monochromator pair for this I parallel, which was this H, that should be equal to I perpendicular, which was this H, that should be equal to I perpendicular into SH, and this guy, it should be I perpendicular into SV. Let me write that. So, I perpendicular into SH, what name you want to give? I here H and here H. So, IHH. For the other one, this is I perpendicular, but this I perpendicular, look here, this I perpendicular is vertical towards the monochromator and detector, right. So, the sensitivity factor what I am going to use is SV. So, this equal to I HV, is it? So, what I can write? I can write I HV divided by I HH equal to SV by SH into I perpendicular by I perpendicular, which is nothing but SV by SH, and that I already have defined as my G value. That I already have defined as my G value. So, what you have to do? You have to simply take these two intensity IHV and IHH. You just take the ratio of these two, you will going to get G. Once you will going to get G, you can readily get this R as I VV minus G I VH divided by I VV plus 2 G I VH, as I have already discussed, right. So, we finish here and we will continue our discussion on the next day. Thank you very much.